The year 2020 will no doubt be a big year for science. It's a new decade, and at times like these, we often take the opportunity to look back and see how far we've come. Scientists who came before us made sure our food and drugs are free from poison and built the devices that make our modern lives possible. So as we forge ahead into the new year, let's take some time to thank the intrepid researchers, volunteers, and even the occasional dog who got us to this point. First up, imagine volunteering to be poisoned in the name of making food safer for everyone. That really happened in the early 20th century. These experiments weren't terribly safe or ethical or rigorous, but they are the reason you can be confident your food doesn't have washing powder in it. Let's go to Stefan for more.
I think we can all agree that food is pretty great. So participating in an experiment where almost all you have to do is eat 3 delicious meals every day for up to a year sounds kinda like the dream. But imagine knowing that hidden in one of the foods, maybe the butter, maybe the freshly picked peas, is a substance that's probably toxic. It sounds unthinkable today, but that was the setup of some of the strangest and most infamous human experiments in American history, known as the Poison Squads. They ran for 5 years starting in 1902, and even though they wouldn't pass any scientific ethics committee today, they were revolutionary at the time because people started to realize that maybe they should make sure the things are safe to eat before eating them. The trials were the brainchild of Harvey Washington Wiley, the head chemist with the US Department of Agriculture. Back then, food additives didn't have to be tested or even put on labels, and he wasn't really okay with the idea that no one in America had any way of knowing what they were actually eating unless they had grown or raised it themselves. Formaldehyde, for example, regularly popped up in milk to keep it from souring. Yeah, the known carcinogen that we use to preserve dead bodies. And you'd also often find borax, a mineral that contains sodium and boron, in meat. It made the meat firmer, which made it seem fresher, especially when combined with an extra pinch of salt and red food coloring. These days, borax is a common ingredient in things like detergent and pesticides. And we're not talking tiny, insignificant amounts of this stuff either. But no one had bothered to investigate whether these additives were actually safe to eat. So with $5,000 from the government, Wiley hired a chef, promised a bunch of otherwise great free food, and recruited a dozen healthy young men as volunteers. He took their weight and vitals, made them collect their urine and feces, and gave them weekly physicals. Then they started with a low dose of a specific chemical and went up, stopping only when the men were too sick to continue. The first Poison Squad tackled borax and its derivative boric acid, because they were so common. At first, the chef hid the chemicals in butter or milk, but the volunteers could taste the metallic flavor and instinctively avoided it, because no one wants to eat butter that tastes like their silverware. Wiley still needed the men to get the right dosage, so he just put the borax in pills for them to pop about halfway through their meals. Bon appetit. The guys on the Poison Squad reported stomach pains and feeling less hungry when they were fed 2 to 3 grams of borax a day. At 4 grams, they became very tired, developed headaches, and couldn't work normally, which sounds like an average Monday to me, but apparently in their case it was caused by the borax. Through other trials, Wiley also found that if they took a lower dose of half a gram a day for long enough, they'd get similar symptoms. Today we know that eating borax can cause tissue damage, which can eventually lead to fun things like vomiting and convulsions. So thanks for saving us from that one, Poison Squad. Thankfully though, almost no one walked away from these experiments with any obvious long-term problems. Wiley also tested copper sulfate, which was added to things like canned peas to make them bright green, as well as formaldehyde, sodium benzoate, and salicylic acid. And while the effects on the men varied, Wiley concluded that none of the additives were safe. Today, any scientist looking back at these trials would be horrified by not only the ethical problems, because giving people potentially deadly substances, even if they know about them, is never okay, but also the poor experimental design. For one thing, the participants knew they were eating a potential poison, which could have easily skewed the symptoms they reported and made them feel more sick than they actually were. Not to mention that for the most part, the experiment had no real control group. In between testing each substance, the squads were given a break for several weeks, but they weren't asked to continue reporting symptoms or to keep collecting their urine or fecal samples. You also can't really conclude much from a small and specific group of people. Wiley thought that if healthy young men got sick, the same chemical would also be unsafe for women and children. It's not really how biology works though, and a few dozen white guys didn't exactly represent all of America. But even though there were a lot of flaws with this experiment, it was the first time somebody thought to test food additives and study them one at a time. Later research that was actually reliable led to almost all of these additives being banned from food, except for sodium benzoate, which is a common preservative in acidic foods like orange juice and soda. But we only use it because we've tested it and it's considered safe. And journalists loved covering the happenings in the DC greasy lab kitchen, so people across the country started thinking seriously about the things that might be used to preserve their food. In 1906, partly because of the public's new awareness, Congress passed the Pure Food and Drug Act, a precursor to today's more rigorous regulations. Those concerns also led to the creation of the FDA, which is the organization that makes sure the ingredients in your food aren't gonna kill you. For the most part anyway. If you decide to crack open 10,000 cans of baked beans, there's not much they can do to help. That one's on you. Since Wiley was so instrumental in protecting America's food, he's often called the father of the agency. So the poison squads were a really horrible idea and full of sketchy science. But because of the progress we've made since then, going to the supermarket today is a whole lot safer.
I don't know, I hear formaldehyde-laced beans are pretty tasty. A lot of our historical episodes have looked at medicine and health. Maybe that's because saving a lot of lives is a pretty good way to be remembered. But it's not just drugs that have changed our lives for the better. Like all the work that went into bringing you the phone that's probably in your pocket right now, or at least somewhere within arm's reach. Before phones, the ubiquitous pocket electronic device was the calculator. Less glamorous, sure. But there's a lot going on with that little 4-function piece of plastic your teachers passed around in elementary school. Here's Hank with more.
We don't think of pocket calculators as being all that special these days. They're cheap, easy to use, and your phone can do all that stuff anyway, right? But the development of the pocket calculator mirrors the electronics revolution that brought us smartphones and modern computers. In fact, some technologies we now take for granted found their first widespread use in electronic calculators in the 1960s and 70s. And the first sort of compact electronic calculators couldn't fit in your pocket. They were the size of a typewriter and demanded so much power that they needed a wall outlet. For example, the Anita Mark VIII was available in the early 1960s and cost as much as a car at the time. It performed basic arithmetic functions by using vacuum tubes, basically airtight chambers with filaments inside, which could shuttle electrons in precise ways to generate currents and act as switches. The name was short for either a new inspiration to arithmetic or a new inspiration to accounting, which gives you a clue as to who bought these expensive machines. But soon, there were a couple major technological leaps that revolutionized calculators and also the rest of electronics and the whole world. First, for calculators to become cheaper, more portable, and less fragile, vacuum tubes were replaced with transistors and integrated circuits. A transistor functions like a gate for electrons. Basically, by applying electrical power, it can either be opened or closed. These binary states are still the basic idea behind all electronics. And typically, transistors are made from a material called a semiconductor, which sometimes conducts electricity and sometimes doesn't. Early transistor electronics, like the super popular transistor radio for consumers, would string individual transistors together in series. Transistors were way smaller and sturdier than vacuum tubes, but more complex devices like computers were still fairly big. In the late 1950s, though, engineers invented the integrated circuit, a single semiconductor chip that had all parts of a circuit on it, including many transistors. One of those engineers worked at Texas Instruments. The company knew it had something good on its hands, but struggled to find a good consumer outlet for these compact chips. That is, until 1965, with the design of the first prototype electronic pocket calculator. It was codenamed Caltech, measured about 10 by 15 centimeters, and could perform the 4 basic arithmetic functions: addition, subtraction, multiplication, and division. Its chip required the equivalent of thousands of transistors. They even built a version for testing without integrated circuits, which, according to one designer, took up an entire 2-tiered, 2-meter tall desk. So integrated circuits really packed a punch. These days, we call them microchips, and we put them in the everything. Caltech also printed out results on a roll of tape using a thermal printer. This was also pretty new at the time and worked by basically melting text into a special type of paper like the receipts you get at the grocery store. The TI team actually wanted an electronic display, but that technology wasn't great yet. LEDs at the time had poor visibility. LEDs work based on passing an electric current or field through a semiconductor, which causes electrons to shift around and emit light. The color of the light can be altered by introducing different elements, which is easier said than done. It's taken decades to make LEDs in every color of the rainbow. Early on, gallium and arsenic-based LEDs were only capable of emitting infrared light and very dim red light because of the way electrons move through those particular elements. Lots of pocket calculators after the Caltech did feature red LED displays, but they demanded a ton of battery power because those early systems weren't very energy efficient. The next revolution in calculators was the liquid crystal display, or LCD. Liquid crystals have molecules that are free to move like a liquid, but can settle into an ordered state like a crystalline solid. Dual identity means they can block or transmit light, and switch between states rapidly when there's an input like electricity. That's why we use them in electronic displays. The first LCDs were fragile and only worked at high temperatures, but a breakthrough came in perfecting a mix of chemicals that behave as liquid crystals at room temperature. Other developments made them quicker and more durable as well. LCDs used less power than LEDs, so calculators could run off a watch battery instead of large battery packs. Alongside digital watches, pocket calculators were the first widespread consumer use of the LCD display. Nowadays, you'll hear about LED and LCD technologies when you're researching what kind of TV you might want to buy. Over the next few decades, calculators became slimmer, cheaper, and more powerful. They evolved from specialized tools for business to a status symbol to a basic tool that you're probably gonna get for free as a promo at an event. That's certainly where I got mine. But all this development eventually slowed to a crawl. So you wouldn't carry a separate calculator either unless you're still in school and need it for the SAT or something. They've stayed basic machines to help with learning, not flashy internet-enabled devices. And that is how the golden age fizzled. But calculators played a huge part in the consumer electronics revolution, popularizing display technology and the computer chip itself. Nothing to sneeze at.
Funny you should mention sneezing. Yes, we're headed back to the world of medicine, specifically the flu. There's a bacterium out there in the world called Haemophilus influenzae, which has nothing to do with influenza. But for a while, scientists thought it did, so they gave it that name. How could they make such a huge mistake? Stefan explains.
If you're coughing, sneezing, or starting to feel under the weather, you might blame a virus, or possibly a bacterium, which is not something humans have known to do for very long. Around 400 BCE, doctors might have blamed an imbalance of the 4 vital humors for your illness. And around the 1700s, they might have pointed to an invisible, disease-carrying fog instead. But today, we know pathogens, viruses, bacteria, and certain other microbes, are responsible for many diseases. But linking specific diseases to the microbes that cause them has been surprisingly tricky. In 1882, a scientist named Robert Koch demonstrated that the bacterium Mycobacterium tuberculosis causes tuberculosis. And in 1890, he also published a framework for future scientists to make similar discoveries. He created a checklist for researchers to reference anytime they're trying to link a pathogen to a disease. The steps are as follows. First, researchers had to be able to find the pathogen in sick organisms, but not in healthy ones. Second, it could be grown in pure culture, which means that a sample of the microbe could be taken from a sick organism, and then the microbe could grow independently in a 19th century version of a petri dish. Third, if they exposed a healthy organism to the stuff that they grew in step 2, that organism would get sick with the same disease. And finally, though this step is sometimes considered optional, the same microbe that was isolated in step 1 must be found again in the organism made sick in step 3. These steps are now known as Koch's postulates. The idea is that if the microbe meets all of the postulates, then you know it's the cause of the disease. Unfortunately, his postulates had a few problems. Take postulate 1. Tuberculosis can actually be found in healthy individuals. That's called latent tuberculosis. So it doesn't meet Koch's first postulate. This situation just didn't show up in his experiments, which were done on guinea pigs. Postulate 3 isn't perfect either. Assuming that any healthy organism exposed to a pathogen will get sick ignores differences in immune systems. A healthy organism might be able to fight off the infection, or might already be immune to the disease. But it was the second postulate that caused the most confusion. Something grown in pure culture has to be the only living thing in the dish, and many pathogens just can't grow independently like that. Viruses, for example, reproduce by hijacking molecular machinery in the cells of the organism they're infecting, meaning you can't grow them in a dish by themselves, but bacteria often grow in a dish just fine. Because postulate 2 required the thing to grow in culture, researchers at the turn of the 20th century would almost exclusively blame bacteria for the diseases they were studying, which resulted in some false accusations. Malaria, which is actually caused by blood-infecting parasites, was blamed on a bacterium from Italian marshes in the 1880s, which they named Bacillus malariae. Canine distemper, a sometimes deadly disease in dogs that causes symptoms like fever and vomiting, was linked to a series of different bacteria before it was finally proven to be a virus in the 1920s. And the familiar influenza, or the flu, was misidentified as a bacterium in 1892 by a colleague of Koch's. The bacterium came to be known as Haemophilus influenzae. To study the flu, researchers needed samples of spit and snot from people with obvious symptoms. But one thing that made influenza hard to study was that even though the flu usually reaches a peak in winter, the only time that scientists could reliably find large numbers of flu-ridden folks at the same time was during a pandemic, and those could be decades apart. So the first chance scientists had to check the results from 1892 was during the next influenza pandemic in 1918, and the researchers were unable to replicate those initial results. But it wasn't clear at the time if it was because of poorly controlled studies and the chaos of one of the worst pandemics in recent history and the end of World War I, or if they were just wrong. A vaccine was developed in New York based on hemophilus, just in case. There was at least one study around that time that managed to find evidence of the right answer. Influenza is a virus. But it took until 1933 and another influenza pandemic for scientists to prove without a doubt that the flu is caused by a virus, thanks to the introduction of ferrets as a model organism. Ferrets were the only small mammals they could find that could actually get the flu and show symptoms similar to ours. So it seemed like Koch's postulates, especially the second, really hindered research into any disease that didn't have a bacterium behind it. But does that mean they're useless? Not at all. Since the 1880s, scientists have tweaked Koch's postulates over time to match modern understandings of pathogens. Today, the focus isn't just on microbes, but on their genes. Using genetic sequencing, scientists can gather information about all of the nucleic acids in a sample, whether DNA or RNA, and then use a modified version of Koch's postulates to figure out which genes are most associated with disease symptoms. For example, in 1996, scientists at Stanford came up with a new set of postulates with 7 gene-centric points. By using gene sequencing, scientists can find pathogens that haven't been isolated and identified before, and there's no need to culture them. Koch's postulates provided a solid foundation for researchers to begin linking diseases to their sources. And sure, there were a few mistakes, but they provided a rigorous testable basis for understanding disease, even if we had to come along and make some changes later, and even if some ferrets had to get the sniffles.
Incremental progress is the name of the game in science. Being wrong is often not a bad thing, at least not with the right attitude. But sometimes it's more about quiet persistence, even when your colleagues think you're wrong. Some scientists are never recognized in their lifetimes, despite saving tons of lives and practically defining their field, like Jon Snow. Not that Jon Snow. Here's Hank to tell us more.
These days, most people are like me. They hear the name Jon Snow and they think of Game of Thrones. Or they think of that British news anchor. But before there was Jon Snow, the news anchor, and before there was Jon Snow, the fan-beloved brother of the Night's Watch, there was Jon Snow with an H, the 19th century medical doctor from England. But Dr. Jon Snow has a few claims to fame, including developing early anesthetics and administering anesthesia for the Queen while she delivered 2 of her kids. But mostly, he is remembered for the way he fought cholera. In the 1850s, his timely action and clever thinking stopped an outbreak, and even though he was never recognized during his lifetime, he's now considered one of the founders of epidemiology. Our story begins in mid-19th century London, which was, in a word, gross. In 2 words, super gross. Like many cities in the 1800s, London saw a huge increase in population, and with that came a huge increase in poop, which nobody knew quite how to deal with. Sewer systems hadn't quite spread to the entire city, so in places like the Soho district, people sloshed their waste into the streets, dumped it into overflowing cesspools, or trucked it over to the Thames River, the river that notably also served as the city's primary water supply. During this period, maybe unsurprisingly, London and the rest of Europe were also being plagued with persistent outbreaks of cholera, a highly infectious, sometimes deadly diarrheal illness. And there was considerable disagreement over why. We didn't know that bacteria and viruses were at the root of most infectious diseases, so the prevailing idea was miasma theory, which said that they were passed around by bad air. This is where Jon Snow came in. He had encountered cholera before in mining populations and had come to believe the disease was not spread by air, but by ingesting stuff contaminated with human waste. After all, the miners brought their meals to work, didn't have a bathroom down there, and probably didn't wash their hands before eating. Gross. When Snow observed the situation in London, he therefore concluded that cholera was being spread by tiny fecal particles in the water, and in 1854, he got a chance chance to prove it. The year before, a new cholera outbreak reached a London borough near Snow's home, and it killed more than 500 people in a matter of weeks. Based on the area, Snow was suspicious of one water pump on Broad Street, specifically after his sample of the water turned up visible white flecks of organic material. So, he obtained a list of some people who had been killed by the outbreak and began talking to their families. And ultimately, he found the common factor was where those victims had gotten their water, that pump on Broad Street. Snow then took his evidence to the local officials, who agreed to take the handle off the pump to prevent people from using it. But even then, nobody really believed Snow about why, including Britain's General Board of Health. It's possible that his sample size wasn't enough to convince them, or maybe it was the fact that he couldn't prove what in the water was causing the illness. In any case, Snow was confident enough in his findings that when other cholera outbreaks appeared, he continued trying to find the contaminated water behind them. And ultimately, that led him to a more citywide discovery. At some point, Snow realized all the districts in London affected by the outbreaks had their water piped in from one of two suppliers, one that got their water from upstream of London and one that got it from downstream. He suspected the downstream water, as you might also suspect, had a bunch of sewage in it, so cholera should have been more common in the neighborhoods that drank it. To prove this, he began rifling through hundreds of parliamentary death records, and he found that areas with downstream water had 14 times more deaths from cholera during the outbreak. Now, to you, and to me, that might seem like pretty conclusive evidence that sewage equals cholera, but for various reasons, the idea still didn't catch on. And that was the end of that, or at least it was Snow's last published attempt at convincing the medical community that sewage caused cholera. He did continue to investigate it privately and do other kinds of research, but unfortunately, he died prematurely only a few years after these events. The thing is, though, Snow was very right. Cholera is typically a waterborne illness spread by sewage-contaminated water. It just took a few more decades of work and proof that microbes can cause diseases for scientists to finally prove and accept that. Thankfully for all of us, though, Snow's methods didn't fade into obscurity. Even if his work was rejected in the 1850s, his outbreak management strategies are still in use today. His idea to map the origin of cases is a technique that is currently saving lives, and it was so unique that it was a foundation of modern epidemiology. Looking back, Dr. Jon Snow may not have had a sword, he may not have had an army at his command, but he did wield mass health information and help shape a major field of science. So even though Snow wasn't celebrated during his lifetime, there's a lot to celebrate about him today, because in the end, there's no doubting that his contributions have helped save millions of lives.
Next, let's look at two serious tragedies that ultimately made our drugs safer. There was a time in the United States that you had to label what was in your medication, but no one regulated what counted as medication, meaning you could sell poison to people as long as you were upfront about it, weirdly enough. And as you might predict, that resulted in a few deaths, but also stronger rules. Here's Stefan to explain what happened.
The history of medicine is full of some huge triumphs, but also some pretty terrible mistakes. Like in the 1930s, a company out to make a quick buck took a safe, effective drug and managed to make it a killer. But surrounding that tragedy are some pretty fascinating stories. How a dye became a wonder drug, how the US FDA became what it is today, and how one scientist walked home with a Nobel Prize. The drug in question is called elixir sulfanilamide, and it was briefly manufactured and sold by the S.E. Massengill Company of Tennessee in 1937. But before this deadly elixir was concocted, sulfanilamide had a good rep as an effective drug all on its own. Sulfanilamide is an antibiotic, so it's used to fight bacterial infections. It works by interfering with bacteria's ability to make folic acid, which they need to reproduce. It was derived from an earlier drug called Prontosil, which had a vivid red color and was actually developed by the dye industry. In 1932, chemist Gerhard Domach found that this molecule wasn't just pretty. It could cure bacterial infections in mice. And once Prontosil hit the market in 1935, it quickly gained popularity and saved a lot of lives. In fact, Prontosil and related compounds were some of the earliest widespread antibiotics. Penicillin had already been discovered, but it wasn't easily available. available yet. And further research showed that there were two parts to the Prontosil molecule. One part was the dye, and the other was the antibiotic. The antibiotic half was sulfanilamide, which researchers found could be used on its own, mostly in powder or pill form. While it had potential side effects, it was generally safe. We actually still use sulfanilamide to treat vaginal infections, though not very often because there are other antimicrobials out there nowadays. The problem was that sulfanilamide had already been synthesized by chemists and the patent had expired, so anybody could make and sell variants of it. Enter the Massengill Company, who found that their customers liked their drugs in syrup form. They set out to make a liquid version of sulfanilamide, and their researchers eventually found that the powder would dissolve in diethylene glycol. At the time, diethylene glycol was known as a solvent. It had a sweet taste and smell, and once the lab added some caramel and raspberry flavoring, they figured they had a nice medicine and released it as an antibiotic elixir. Frankly, it sounds tastier than some of the cough syrups I've had, except for one thing. Diethylene glycol is super poisonous. Back then, there were 1 or 2 scientific studies about its toxicity, but they weren't widely known. These days, it's used as antifreeze, among other things, and we know it's not a sweet treat. Inside your body, diethylene glycol takes time to do its dirty work. At first, the symptoms resemble drunkenness, but after several hours, the poisoning gets worse. While scientists aren't exactly sure how it kills, we do know it gets broken down by your liver into a nastier form. From there, it shuts down the kidneys and can affect the nervous system too. The instructions that shipped with the deadly elixir sulfanilamide said to keep giving it to patients until they got better, which means that some people were poisoned by well-meaning loved ones who fed them antifreeze for days or weeks until they succumbed, usually from kidney failure. In total, at least 105 people died. And if Massengill had just fed it to a handful of mice before shipping a bunch of it out, this tragedy might have been prevented. Before 1938, the US FDA only had the power to prevent adulteration and mislabeling. You couldn't, for example, sell tablets of flour and say it was medicine. That was against the law. But you could sell something that was poison with zero safety testing beforehand, as long as it was what you said on the label. The Massengill Company's elixir contained exactly what they said it did: sulfanilamide and diethylene glycol, with some water and flavoring. But they did technically break the law. They called the stuff an elixir, but that word was only supposed to be used for products that contained ethyl alcohol, and Massengill syrup had none. The FDA seized on this technicality. They used it to track down the tainted medicine and slapped Massengill with an unprecedented fine. If not for the fine print, they would have been helpless and many more people could have died. But a new law was rushed through Congress in 1938, giving the FDA increased power over drug safety. That law is credited with preventing the infamous drug thalidomide, which was found to cause severe birth defects, from hitting the US shelves many years later. In the aftermath of this tragedy and new legislation, the chemist responsible for the antifreeze elixir committed suicide, and the senator who sponsored the 1938 drug law died shortly after it passed, reportedly of exhaustion. Powder and pill forms of sulfanilamide were still being made in labs and widely used as antibiotics by American soldiers in World War II. As for Gerhard Domach, developer of Prontosil, he won the 1939 Nobel Prize in Physiology or Medicine for helping to usher in the antibiotic era. Because really, Prontosil, sulfanilamide, and related compounds were used a lot at the time and can be safe and effective antibiotics. You know, as long as you don't take them with antifreeze.
Stefan mentioned thalidomide, and he's got that story too. Here's how incredibly subtle differences in chemistry can sometimes mean life or death.
On October 1st, 1957, a new over-the-counter drug was introduced in West Germany that was supposed to basically cure morning sickness during pregnancy. It was called thalidomide. Thousands of women purchased the drug and were relieved when their morning sickness disappeared. And everything seemed great until later the next year, when thousands of infants were born with severe birth defects, like brain damage and deformed limbs. Doctors noticed the surge, but at first they couldn't figure out what was causing it. Then, 2 doctors, Wiedekind Lenz from Germany and William McBride from Australia, both noticed that the mothers of these babies had all taken that amazing new morning sickness drug. By 1961, Lenz had proven the link between thalidomide and the birth defects, and it was pulled from the shelves. But by then, thousands of infants had been born with those birth defects, and nearly 40% of them had passed away. Rules for drug testing weren't as strict back then, and in this case that cost thousands of lives. Even though they were now aware that thalidomide was a problem, scientists still didn't know why. It turns out the answer lies in its chemistry, or more specifically, its geometry. What researchers didn't know at the time was that there were actually 2 versions of the thalidomide molecule. Thalidomide, which is made up of 3 connected rings of carbon and nitrogen atoms, plus some oxygen and hydrogen, is what's known as a chiral molecule. Chiral comes from the Greek for hand or claw, And chemists often think of chiral molecules as being right-handed or left-handed. And that's because the different versions of chiral molecules, called enantiomers, are made up of all the same parts but arranged differently, just like your hands. If you try overlaying your right hand on your left, you'll see that no matter which way you turn your hands, you can't make them match up. Even if you make your thumbs line up, one hand is palm up and the other is palm down. In other words, both hands have the same 5 fingers, but they're not identical. And molecules like thalidomide are the same way. A chiral molecule has an atom, typically carbon, with 4 different groups attached to it. That's called the chiral center. A group can be anything from a single atom to a long chain to rings. In some cases, 2 groups can even be connected. These groups are kind of like your fingers. In each enantiomer, the groups are attached to the chiral center in the opposite order, so they're mirror images of each other. In thalidomide, for example, the chiral center is a carbon atom attached to one of the rings. It's bonded to 2 other carbons, a nitrogen and a hydrogen. If you position the version of the molecule that's considered right-handed, called the R enantiomer, so the closest oxygen atom to the chiral center is below it, the hydrogen atom attached to the center will be facing away from you. But if you position the left-handed or S enantiomer the same way, the hydrogen atom will be facing toward you. In other words, the 2 enantiomers are mirror images of each other. And because different receptors and enzymes in your body react with molecules in very specific ways, the fact that enantiomers are mirror images means that they might react to things totally differently. In the case of thalidomide, scientists discovered that the R enantiomer helped with morning sickness, but the S enantiomer caused those severe birth defects. One of the most famous, or maybe infamous, examples of how 2 enantiomers affect the human body is methamphetamine. You'd probably associate that name with the street drug, but the molecule can only really break bad when it's in its R formation. The S enantiomer is commonly sold over the counter as a vasodilator, and you can easily find it in vapor inhalers. But the vapor inhaler you just bought at the pharmacy isn't filled with a dangerous drug, because the S version will never be psychoactive. After researchers discovered that only the S version of thalidomide caused birth defects, they thought about isolating the R enantiomer so they could continue to use it to treat morning sickness. But it turns out that thalidomide's R enantiomer can actually switch to the S version while inside the human body, meaning that even if they'd isolated 100% pure R thalidomide, it still wouldn't be safe for pregnant women. But in 1998, the FDA did approve thalidomide, almost 40 years after rejecting it based on the birth defect problems. This time, though, it was approved for treating complications from Hansen's disease, aka leprosy. And recent research is also leading some scientists to believe that in certain cases, thalidomide could help with a number of debilitating diseases, including some forms of breast cancer. They just make sure not to prescribe it to anyone who's pregnant.
I hope you're all enjoying this showcase of Stefan's shirts, by the way. Does he call dibs on all the history episodes? Oh wait, here's one from me. It's about a deadly disease, a desperate race, and one very, very good boy. Even if you're not big on Alaskan history, you might have heard of the Iditarod sled dog race. Every year since 1973, people have raced their dog teams across the 1,500-kilometer stretch of Arctic tundra between Anchorage and Nome, Alaska. The race starts on the first Saturday in March, and to win, participants have to charge through some of the harshest conditions in the Northern Hemisphere. But it's not an exercise in torture. It's inspired by what's sometimes called the Great Race of Mercy, where dog sled teams raced along much of the same trail to deliver an antitoxin that would save thousands of people from a deadly diphtheria outbreak in the winter of 1925. In the early 1900s, most of Alaska's remote towns were pretty much inaccessible during winter. Train tracks connected the largest cities, but the most reliable way to travel between most places was by dog sled. Driven by so-called mushers and pulled by teams of dogs, these sleds were used to transport people, goods, and mail during the long winters when the severe weather knocked boats and planes out of commission. In January 1925, that dog sled transportation network became one town's last hope. In December of 1924, Curtis Welch, the only doctor in Nome, Alaska, was treating an outbreak of sore throats and coughs in the town's children, which he initially diagnosed as tonsillitis, a simple viral infection. When 2 of his patients died, he realized he was facing something much more serious: diphtheria, an extremely contagious disease caused by the bacterium Corynebacterium diphtheriae. It spreads through tiny droplets of mucus coughed or sneezed out by infected patients, which linger in the air and on surfaces. At first, the disease looks a lot like tonsillitis or even a common cold, but it's way more deadly because the bacteria invade the patient's upper respiratory tract and produce a type of cell-slaying protein known as an exotoxin. Once it makes it into host cells, the exotoxin protein keeps them from manufacturing their own proteins, which rapidly rapidly kills them. As dead and dying cells slough off the victim's nose and throat and mix with the growing bacterial colonies, they form these thick, leathery gray coatings called pseudomembranes. They can make it hard to swallow or even breathe, and without treatment, the disease kills more than half of its victims. But even back in 1924, it could be treated. Scientists would inject diphtheria into animals that were less susceptible to the disease, then collect the antibodies they produced in response, and use them to make an antitoxin serum. When it's treated with the antitoxin, the death toll from diphtheria drops to 1 in 10. Unfortunately for the residents of Nome, the town's supply of antitoxin had expired, and the vaccine, developed in 1921, hadn't been administered widely. To keep the outbreak from getting even worse, Welsh put the entire town under quarantine to reduce the spread between families and keep the disease from reaching the roughly 10,000 people in the rest of the region. But without the antitoxin, thousands of people were at risk of infection and death. A national search found a suitable supply of the antitoxin in Anchorage, Alaska, but no one was sure how to get it to Nome. The closest trains brought it to Nenana, which is still more than 1,000 kilometers away. Planes back then were open cockpit, and with the worst weather in 20 years, they weren't an option. And sea ice blocked the shipping route. So the governor of the Alaskan Territory turned to 20 of the best mail-carrying dog sled teams to take the precious serum on the last leg of the journey. Over 5 days, 20 mushers and 150 dogs carried the 9-kilogram package of antitoxin between relay points, fighting whiteout blizzard conditions and temperatures of negative 45 degrees Celsius across a trail that normally took 3 to 4 weeks to complete. 4 of the animals died in the process. The teams averaged about 48 kilometers each, although some went much farther than others. Leonard Sapala and his lead dog Togo traveled 146 kilometers over the tundra and crossed the icy surface of the frozen Norton Sound. The last team, led by musher Gunnar Kaysen and his lead dog Balto, made the trek to Nome in a whiteout so bad that Kaysen said he couldn't see any of his dogs. He relied on Balto's sense of smell to guide them. They reached Nome in the early morning of February 2nd, just 5 days and 7 hours after the serum was picked up by the first musher. Thanks to the rapid delivery of the antitoxin, only 5 of Nome's 1,400 residents died during the outbreak. The national publicity of Nome's dire situation fueled a campaign by health officials to widely vaccinate against diphtheria in the United States, and that continues today with the Tdap vaccine. In the 1920s, there were 100,000 to 200,000 cases and 13,000 to 15,000 deaths from diphtheria every year. But the US has only recorded 5 cases in the last decade, and the state of Alaska still runs a yearly immunization drive alongside the commemorative Iditarod sled dog race. So, in a way, those 20 teams saved an uncountable number of lives. All dogs are good dogs, but these guys were the best. Finally, I said before that historical episodes like these are why our food and drugs are free from poison. Notice I didn't say drinks, because if you want to be technical, alcohol is a poison. But there was a time when the US government made it more poisonous. Once more, here's Stefan to tell us why they thought that was a good idea.
On Christmas Eve 1926, more than 60 people ended up in a single hospital in New York City. They were violently ill and hallucinating, and despite doctors' best efforts, within a few days about half of them died. But it wasn't a virulent flu or poorly chosen mushrooms that caused their deaths. It was alcohol that had been poisoned by the US government, which sounds like a conspiracy theory, but it's the truth. In the 20s, a chemical war between government regulators and illegal booze sellers resulted in tens of thousands of poisonings and hundreds, maybe even thousands of deaths. In the US, the roaring 20s were a decade filled with jazz, flapper dresses, speakeasies, and lavish parties like the ones in The Great Gatsby, even though America was supposed to be a dry country. The 18th Amendment, which banned the production, sale, import, and export of alcoholic beverages, came into effect in 1920, and it wasn't repealed until 1933. But plenty of people still drank, even though that sometimes meant risking their lives. When alcohol became illegal, people turned to the black market for their booze. And thanks to heavy enforcement at ports of entry, smugglers could only bring in so much. So the bootleggers that trafficked in illegal alcohol often stole industrial alcohol instead. Ethanol, the main kind of alcohol in alcoholic beverages, is used in everything from cosmetics to pharmaceutical products to house paint. But at the turn of the century, import taxes made it really expensive to use pure ethanol that way, because it's technically drinkable. So starting in 1906, almost 15 years before Prohibition, the US government began adding toxic chemicals to industrial alcohol alcohol to make it cheaper, a tactic already used in other places like Europe. Industrial formulas were spiked with well-known toxic compounds like gasoline, chloroform, and methanol. And because that made them undrinkable, when the 18th Amendment went into effect, they weren't covered by the ban. But for the most part, all one had to do to make them drinkable was distill them. That's the process where alcohol is boiled and then its vapor is collected and cooled. And when done carefully, it can get rid of small amounts of toxic additives if their boiling points are different from ethanols. During the first several years of Prohibition, the US Treasury Department estimated tens of millions of gallons of industrial alcohol were stolen for human consumption. So in 1926, President Calvin Coolidge used the help of chemists to make these already toxic alcohols even more dangerous, particularly by adding methanol. There was already some methanol in most industrial alcohol formulations, but the government added more, a lot more, to the point where it was sometimes 10% of the entire product. And that change is probably what caused so many poisonings and deaths. No alcohol is great for you, but methanol is much worse than ethanol. The two chemicals only differ by a carbon and two hydrogens, but that's enough to make one drinkable and the other lethal. In your liver, an enzyme called alcohol dehydrogenase removes hydrogens from alcohols. Ethanol is converted to acetaldehyde and then eventually to acetic acid, the same stuff in vinegar. Methanol is also processed by this enzyme, but the losses of hydrogens create formaldehyde and then formic acid instead. And formic acid is bad! It inhibits a key enzyme that your cells need to convert sugar and oxygen into usable energy. So even though they've got plenty of food, your cells basically end up starved. That's why the buildup of formic acid in someone's body can cause a range of horrifying effects, from holes in the stomach and intestines to vomiting blood and kidney failure. One of the most common symptoms, though, is hallucinations, like the ones experienced by all those people rushed to that New York hospital in 1926. That's because your optic nerves, the nerves that transfer visual information from your eyes to your brain, need a lot of energy to function, so they're among the first to feel formic acid's toxic effects. And that damage can be permanent, which is why methanol poisoning frequently causes blindness. Now, in principle, even 10% methanol can be distilled away, but the bootleggers' chemists didn't have the best equipment, and they were pressed to work quickly. And since booze was illegal, no one was checking their product to make sure it was safe. Although the exact figures aren't known, by the time Prohibition ended in 1933, some estimate that over 10,000 people had died from drinking government-poisoned alcohol. Killing people wasn't the goal, but it was the result. And these deaths became a hot-button political issue. So as the 20s came to a close, regulators slowly started switching to less toxic dyes and noxious compounds that couldn't be distilled away. For example, in 1930, the US government announced the discovery of alkotate, a sulfurous compound that smells like rotten eggs, which isn't exactly an appetizing scent for a gin and tonic. Some industrial formulations still included methanol, and some still do today, but when the 18th Amendment was repealed, there was much less incentive to drink them. So nowadays, thankfully, methanol poisonings in the US are relatively rare.
Thanks for watching this SciShow compilation, which was brought to you with the help of our patrons. If you like what we do here and you want to help us bring cool stories like the ones you just saw to everyone, check out patreon.com/SciShow.